Okay, thank you all for being here. So what we want to do today is introduce two puzzles. One is really going to be a warm-up for the main puzzle. These puzzles are going to involve infinitely many clowns, and each of them is going to consist of a short mathematical argument which leads to some really surprising conclusions. Okay, so the math behind these puzzles is going to be pretty straightforward. I'm going to explain it all in today's lecture, but it turns out that thinking about what's going on in these puzzles is quite philosophically interesting. Okay, so let's start with our warm-up puzzle. So in our warm-up puzzle, we have infinitely many clowns, and these clowns don't have unlimited powers, but they do have one very special talent. Their very special talent is they can walk into a room and they can put some balloons in that room really, really quickly as you want. Okay? So now we have our room between, and I'll tell you what goes on in this room between noon and 1 p.m. Okay, so at 1 p.m., clown number 1 comes into the room. But before that, at 12:30, clown number 2 comes into the room. Before that, at 12:15, clown number 3 comes into the room. Before that, at 12 and 7.5 minutes, clown number 4 comes into the room, and so on. Okay, so just a few things to note about the setting. All infinitely many clowns come into the room between noon and 1 p.m. And one slightly confusing feature of the setup is the clowns with the smaller numbers are going to come in later, right? So if you think about it, for each clown, all the clowns with larger numbers than it are going to arrive before. And this also means that when each clown comes in, there have already been infinitely many clowns that have come into the room. Okay, now each of these clowns has a plan, and their plans all look the same. So each clown says to themselves as following, when I come into the room, if there are no balloons in this room when I come in, then I'm going to put some balloons in the room, and I'm going to do it quickly enough so the balloons are already there by the time the next clown arrives. Okay? Otherwise, if there are already balloons in the room, the clown doesn't put any balloon, they just go home and do nothing. Okay. One side thing to note, all balloons featuring in our talk today are really, really good quality balloons. They're not going to pop or disappear at any point during our puzzles. Okay, so sometimes we make plans, but we don't manage to follow through with them. So I once planned to run a half marathon, but sadly, I couldn't really find the time to train, and I was also a bit lazy, and I never followed through with my plan. Okay? But in this case, it looks like for these clowns, these plans are pretty easy to carry out, right? Each of them just comes in at a certain time. They just check if there are balloons. If there aren't, they put some. If there already are, they do nothing. So it looks pretty easy. So let's suppose that all of our clowns have indeed followed through with their plans. Okay, so I want to make two claims about our situation. The first claim is that at every single point, at every single time between 12 and 1, there must be balloons in this room. Okay? Why is that? Let's suppose by contradiction that there is some time where there aren't any balloons in the room. Just suppose that 12:30. Okay, so suppose this purple time, 12:30, is a time where there are no balloons in the room. And now let's think, what happens in the previous time of this series, 12:15, indicated in green here. Okay, so one option is at 12:15, there already are balloons in this room. Okay, but if at 12:15 there already are balloons in this room, remember I said these balloons are very resilient, so if at 12:15 there are balloons, they're still going to stick around until 12:30, which contradicts our assumption that at this purple time there are no balloons. Okay, so there can't be balloons in the room at 12:15. But now let's think what happens when the clown of the green time, in this case clown number 3, walks into the room at 12:15. Right? Clown number 3, remember his plan. His plan is check if there are no balloons in the room. We've just shown there are no balloons in the room. So according to the plan, clown number 3 puts some balloons in the room and puts them so they're there in time for 12:30. Okay? But this again contradicts our assumption that there were no balloons in the room at 12:30. Okay, so we've reached a contradiction either way. So this shows that there must be balloons in the room at 12:30. But of course, 12:30 was just an arbitrary time. The same argument would work whichever time you choose. So this shows that at every time between 12 and 1, there are going to be balloons in the room. Okay, here's the second claim. The second claim is none of the clowns put those balloons in the room, right? None of the clowns put any balloons in the room between 12 and 1. Why is that? Well, let's just pick any arbitrary clown, say clown number 3 coming in at 12:15. So again, remember the clown's plans. Clown number 3 comes into the room, checks if there are balloons in the room. Well, we know there are balloons in the room at every single time between 12 and 1, so there are going to be balloons in the room at 12:15. So according to the plan, clown number 3 isn't going to put in any balloons. And again, clown number 3 was just a completely arbitrary choice. The same is going to be true of every single clown. Okay, so if you step back a bit, you'll notice that these two claims seem to show something pretty weird, right? We have these clowns. All they've done is form these pretty simple plans to come into the room, check if there are balloons, put them there if there aren't any balloons, and they carry out these simple plans. And by doing that, they have somehow managed to ensure that there will be balloons in this room without any of them having put them there. Okay, that's pretty weird. Okay, if you think this is weird, wait till you get to our second puzzle. Okay, so here's our second puzzle. In this puzzle, we still have the same set of infinitely many clowns. They still come into the room at exactly the same times, but this time they have a slightly different plan. Okay, so here's how their plans look. Each clown says to themselves, I'm going to come into the room, and if first there's no ice cream mountain outside the room at noon, and second, no clown that came earlier has put some balloons in the room, then I'm going to put some balloons in the room. Okay? Otherwise, if there either is an ice cream mountain there or some previous clown has put balloons in the room, then they won't put any balloons, they won't do anything. Maybe this room is fun enough as it is, they don't need to bother with it. Okay, so again, these plans don't seem particularly hard to follow for these clowns. Come into the room, check these two conditions. If they apply, they put some balloons, otherwise they do nothing. So again, let's suppose they've all succeeded in carrying out their plan. Okay. I claim that this time it follows that there must be an ice cream mountain outside the room at noon. Okay, so the argument here is just a little bit trickier, but let's go through it. Okay, so let's suppose by contradiction that there is no ice cream mountain outside the room at noon. So we have two options, right? either no clown has put any balloons between noon and 1, or some clown has put in some balloons. So I'm going to consider each of these options and show that either way we reach a contradiction. So first, suppose that no clown ever puts any balloons in the room. Okay, so now think what happens when, for example, clown number 3 comes in at 12:15, right? And again, remember the plans of these clowns. So this clown comes in. She's going to check if there's no ice cream mountain. We're good. We're assuming there is no ice cream mountain. And then she's going to check if no clown that came earlier has put balloons in the room. Well, if no clown ever puts balloons in the room, then this means no clown that came before 12:15 puts balloons in the room. So both of the conditions are satisfied. So our clown is going to put balloons in the room. Okay, but this just contradicted our assumption that no clown ever puts balloons in the room. Okay, so this assumption has led to a contradiction, so we can rule it out. What about the other option? Suppose that some clown does put balloons in the room. Okay, so let's suppose, for example, it's clown number 2 at 12:30. Okay, so one thing to note is we know the plans of these clowns. We know the only situation this clown would have put balloons in the room is first, if there's no ice cream mountain. Good, that's what we're assuming. And second, if they're the first to put in balloons, right? No clown that came in earlier has put in any balloons. Okay, so let's assume that's satisfied as well. But now let's think what happened at 12:15 when clown number 3 came in. When clown number 3 came in, clown number 3 first checked there's no ice cream mountain. Indeed, there's no ice cream mountain. And then they checked if no clown that came earlier has put in any balloons, right? If no one before 12:30 has put in any balloons, then it's also true that no one that came before 12:15 has put in any balloons. Okay, so according to the plan, clown number 3 is going to put some balloons. Okay, but that contradicts what we said about clown number 2 being the very first to put in balloons. Okay, so this option leads to a contradiction as well. Okay, so this was all a little complicated, but let's summarize. We supposed that there's no ice cream mountain outside the room at noon, and we showed that either way we reach a contradiction. Okay, so this means our assumption was wrong, and there must be an ice cream mountain outside the room at noon. But now think how weird this conclusion seems to be, right? We have, again, these clowns forming these simple plans about putting or not putting balloons in the room, and just by making and following through with these plans, they've managed to ensure the existence of something completely unrelated to their powers of putting in balloons. And in fact, they've managed to ensure that it's going to be there before any of them have even arrived into this room. And to make things even a bit weirder, if you think about how our proof went, you'll realize nothing in the proof depended on the clause in their plan really being about ice cream mountains, right? So we could easily amend their plan so that we replace the clause about ice cream mountains with a clause saying that there is world peace at noon. And now it looks like, just by forming these plans about balloons and following through with them, the clowns have managed to ensure there's world peace at noon. And to make things worse, we can even replace it with the condition that 2 + 2 = 5. And now it looks like the clowns have managed to ensure that 2 + 2 = 5. Okay, so something seems to have gone very wrong here. Okay, so what has gone wrong? The argument was a little bit complicated. Maybe we made a mistake in the reasoning. I'm going to suggest that's not what went wrong. The logic and mathematics of our argument was perfectly impeccable. Okay, but this is where it's the philosopher's turn to chip in. And what I'm going to claim is that when we understand what's really going on in these cases, we'll first realize that actually these conclusions are not quite as weird as they initially seem, and that realizing why they're not so weird is going to lead to some pretty important philosophical observation. So here's the first thing I think we should observe about this puzzle. Okay? So suppose indeed the clowns have managed to carry out their plans as we've assumed, and we've just proved this entails there must be an ice cream mountain outside the room at noon. I think part of the reason that this seems so puzzling is that we're assuming that in this case, it means that the clowns have somehow made it the case or caused the ice cream mountain to appear there. Okay? But our proof didn't show any such thing, right? Our proof only showed that the fact that the clowns succeed entails that there is an ice cream mountain there. It doesn't show that the clowns have caused it to be there. Okay? And we can see the distinction between the two with a really simple example. So suppose I make a plan to kick a ball across a field at noon, and suppose I manage to carry out my plan. From the fact that I succeeded, we can infer that there was a ball there and there was a field there. Okay? But me forming this plan or carrying out this plan didn't in any way cause the ball or the field to be there. Okay? The ball and the field were merely necessary conditions for my success. Similarly, I want to claim with the clown's case, when the clowns succeed, that entails that there must be an ice cream mountain in the room at noon. Okay? And when there is no ice cream mountain, the clowns have no hope of succeeding, okay? But this doesn't show that when they do succeed, they have somehow caused this background condition to hold. Okay, so this lesson that we've just learned turns out to be very relevant to a discussion of a problem that's much more important than an obscure puzzle about infinitely many clowns. So some of you may have heard about the problem of free will and the worry that determinism entails that we can't act freely, okay? And philosophers have tried to think really hard about this problem, really carefully, and tried to figure out, is it really true that determinism conflicts with free action? Okay, and what I want to talk about briefly is one very influential argument called the consequence argument that attempts to show that there really is a conflict, there really is a tension between determinism and free action. So to set things up, suppose at a certain time t, say May 1st, 2024, I perform some action. I raise my arm. Okay? Here's what determinism says on at least one standard understanding of the view. Let S be the state of the entire universe a long time ago, say 3 billion years before I was born. Okay? Let L be all the laws of physics, and I really mean all the laws of physics, not just the ones that our colleagues in the physics department have already discovered, but all the true laws that are there to be discovered. What determinism says, that the conjunction of the state of the universe at this early time and the laws of physics together entail everything that happens in the universe throughout history, including the fact that I raise my arm at t. So now suppose determinism is true, and ask yourself, if it's true, could I have acted any differently at t? Could I have not raised my arm at t? Okay, so the consequence argument attempts to answer this with a no. If determinism is true, I could not have failed to raise my arm at t. And here's why. The thought is this. Look, if determinism tells us that the conjunction of S and L entail that I raise my arm at t, then if there's some situation, some possibility where I don't raise my arm at t, that means that's a situation where the conjunction of S and L are false. Okay, so this means that if I manage to act differently, if I manage to not raise my arms, I've somehow managed to make it the case that the conjunction of S and L is false, okay? But it doesn't look like I have any such powers, right? I can't control what happened in the universe 3 billion years before I was born, and sadly, I also cannot control what the laws of physics are like. So it really looks like this is something I can't do. So the argument concludes, this shows that I really could not have acted any differently, which on a certain understanding might make you think that my action wasn't free. Okay, so this is a very compelling argument, but I'm going to suggest that our discussion of the clown puzzle should tell you there's a crucial flaw in this argument. So to note the crucial flaw, I want you to focus on this premise, that if I manage to act differently, then I manage to make S plus L false. Okay, and I want to remind you of the lesson we learned from the clowns. Okay, so let's be clear. What determinism tells us is that if I don't raise my arm at T, that entails that the conjunction of S plus L is false. But that does not mean that in that possibility where I don't raise my arm, I have somehow caused it or made it the case that S plus L is false. Okay, so again, remember, actions can have necessary conditions for the success. In order to kick the ball, there has to be a ball there. In order for the clowns to carry out their plans, there has to be an ice cream mountain. And in order for me to not raise my arm at T, it has to be the case that the conjunction of S and L is false. But it doesn't mean that when it is false, I have somehow made it the case that it's false. Okay? There is a lot more to say about the problem of free will, and there might well be other arguments for thinking that free will and determinism are incompatible, but this argument, at least, is very problematic. So our discussion so far focused on the case where things go well for the clowns, right? There was an ice cream mountain outside the room, and that meant they were able to carry out their plans. But I now want to focus on the other case, right? The case where there was no ice cream mountain outside the room at noon. Okay? So we know from our proof that this means that the clowns did not all succeed in carrying out their plans. Okay? At least some of them must have failed. But this raises a really puzzling question. The question is, what exactly is preventing them from succeeding, right? Remember, these plans are really easy to carry out. Each of them comes into the room, checks if there's no ice cream mountain, checks if someone else has put in balloons. Otherwise, they put some balloons in, right? They're coming into the room. They're trying to carry out the plan. Is there some special, magical force that they're trying to put their balloons and it's preventing them? Or maybe there is a sort of officer of the logic police rushing in to stop them from carrying out their plans. Okay? And just to see how puzzling this is, I do want to note that this contrasts with my analogy of the case of planning to kick the ball. Okay? So similarly, we know that if I plan to kick a ball and there's no ball there, I'm going to fail. But in that case, it's very easy to explain why I'm going to fail, right? What's stopping me from kicking a ball? There's no ball there. Very easy to understand, right? In this case, it's hard to understand what's making these clowns fail. Okay, so to better understand what's going on here, I want to focus on a slightly simpler case. So this case will only have 2 clowns. And here's the plan of clown number 1. Clown number 1 plans to ensure that at noon there are exactly 3 balloons in the room. Here's what clown number 2 plans. Clown number 2 plans to ensure that there are exactly 2 balloons in the room at noon. Okay, Now, I want you to put your hand up if you think they're both going to succeed in their plan. They're both going to manage to follow through. Okay, I want you to put your hand up if you think at least one of them is going to fail in their plan. Okay, good. So you're all right. We know that at least one of them is definitely going to fail in the plan. But here's the following question. Which of these clowns is going to fail in this plan? So put your hand up if you think it's clown number 1 that's going to fail. Okay? Put your hand up if you think it's clown number 2 that's going to fail. Okay? Okay, put your hand out if you think it's complicated or we're not sure or, okay, good. So the answer is we can't really tell, right? There aren't enough facts in the description of the case, right? We know that at least one of them is going to fail, but we don't know which one, and we also don't know why. And there are lots of different ways for this story to unfold, right? Maybe they both come into the room at the same time, really determined to carry out their plans, and they're having a sort of wrestling match to see which one wins over, and clown number 1 is stronger and manages to carry out their plans. Or maybe as they were rushing to towards the room at noon, a green monster came and abducted clown number 1, so they never made it to the room. Okay, but there are also some very undramatic ways they can fail, right? They can both arrive to the room at noon, and clown number 1 suddenly remembered that she's really hungry and decided to go off and buy a pizza. Or maybe they both arrived to the room at noon, but clown number 2 was really tired and fell asleep before they had a chance to carry out their plans. Okay, there can be many, many, many ways this story could go. The only thing we know from the logic of the situation is that there's one way this story is not going to go. They're not going to both succeed in their plan. So back to our ice cream mountain, I want to suggest that exactly the same thing is true of our clowns, right? We know from the logic of the situation that if there's no ice cream mountain, okay, at least some of the clowns are going to fail. But there are many, many different reasons they might fail, right? Some of them are dramatic, like a monster abducts clown number 452 just before they come into the room. But there are also some very boring things that can happen, right? Clown number 7013 might get hungry and go buy pizza or fall asleep before they manage to carry out their plans. Again, here too, there are many different ways for this story to unfold. The only thing we know from the logic of the case that did not happen is that they did not all manage to carry out their plans. In this case too, it turns out this lesson, namely that there are many different ways for the clowns to fail, turns out really important for another very interesting philosophical puzzle, this time concerning time travel. So this is called the grandfather paradox, and it goes like this. Okay, so consider this guy, Tim. Tim is a young man in 2020. Here is Tim 20 years earlier being born, so he's a baby and his mom is holding him. Here is Tim's mom being born. So now Tim's mom is the baby, and the guy holding her is Tim's maternal grandfather. And here is Tim's grandfather a few years before Tim's mom, as a young man, a few years before Tim's mom is born. Okay, so back to 2020. Here's Tim in 2020. He's thinking about his maternal grandfather, and Tim really, really hates his grandfather. He hates him so much that he decides to take a very extreme measure. Okay, so the extreme measure is he builds a time machine. He takes a gun with him, and he travels back in time all the way back to 1975, where he plans to kill grandfather. Okay? So suppose he's practiced, he has his gun, he's a really good shot, he's practiced this, he travels back in time and manages to kill grandfather. Well, now we have a problem, because if Tim killed grandfather in 1975, then Tim's mother wasn't born in 1980, and Tim wasn't born in 2000, and so Tim isn't around in 2020 to form all this plan about building a time machine. So in fact, he never built a time machine and traveled back in time. So no one traveled back in time and killed grandfather. Okay, so we've reached a contradiction. Okay, so the conclusion is we can just tell from the logic of the situation that there's no way that Tim succeeded in traveling back in time and killing grandfather. But here is the puzzle. Why didn't he succeed? Why can't Tim travel back in time and kill grandfather? What's stopping him? Okay, so one very obvious answer you might have at this stage is, unlike the clown's plan, which were very simple, this is quite a complicated plan, right? It's quite hard to build a time machine and travel back in time. So one thing that might be stopping him is you just can't travel back in time. Okay, and indeed, many philosophers have concluded from this puzzle that what it shows is that time travel is impossible. Okay, but the logic of the situation doesn't quite force that conclusion on us, right? It doesn't say that it's impossible to travel back in time. It just says that if Tim travels back in time and attempts to kill grandfather, Tim is not going to succeed. So let's suppose Tim really did travel back in time. Again, we're faced with this worry. Why is it that he can't succeed? What's going to stop him? Is it that when he shoots grandfather, there's going to be a special force stopping the bullet mid-air? Or again, the sort of logic police will rush off to arrest him just before he manages to shoot grandfather. So remember the lesson we just had from the clown puzzle, right? What that lesson tells us is that there are many different ways that Tim could fail. Some of them might be as dramatic as a policewoman rushing in and knocking Tim over just as he's about to kill grandfather, but there could be many, many very boring reasons, right? His gun gets jammed, or grandfather's train is late and he just misses the shot, or all sorts of different mundane things can happen, okay? The story can unfold in many, many different ways. The only thing the logic of the situation tells us is there is one way it's not going to unfold. It will not unfold by Tim, in fact, killing grandfather. Okay, let's move to our final lesson. So when people hear about this clown puzzle, a very common reaction is to think that this shows that there's something really mysterious and spooky about infinity. Okay, and to be fair, the logic of our puzzle really did depend on there being infinitely many clowns. Okay, so let's just quickly see why. Suppose we had exactly the same puzzle, except now we have finitely many clowns, say 3 clowns, okay? And they make the same plans. Now we're not going to be able to prove that there must be an ice cream mountain there, right? Suppose there's no ice cream mountain, there's going to be no contradiction. We'll just have clown number 3 is going to be the first one to come in at 12:15. They're going to check no ice cream mountain, good. They're going to check that no clown that came earlier put any balloons. There weren't any clowns earlier, fine. They're going to put some balloons. Then at 12:30, clown number 2 is going to come in. They're going to see someone else has already put some balloons. They're going to do nothing. At 1, clown number 1 is going to come in. They're going to see some earlier clown has already put up some balloons. They're going to do nothing. And that's it, right? No contradiction. Everything is fine. We can't conclude that there has to be an ice cream mountain. Okay, so our original puzzle really depended on us having infinitely many clowns. But I want to suggest that there are variants of this puzzle that involve only finitely many clowns. Okay, so here's a variant. here's a variant that involves just 2 clowns. Okay, so clown, oops, sorry. Okay, so we have just 2 clowns, and clown number 1 plans to ensure that at noon, either there is an ice cream mountain outside the room, or there are exactly 3 balloons in the room. Okay? Meanwhile, clown number 2 plans to ensure that either there's an ice cream mountain in the room at noon, or there are exactly 2 balloons in the room at noon. Okay? And it follows from the fact, if both these clowns succeed in carrying out their plans, right, it's going to follow that there must be an ice cream mountain outside the room at noon. Why is that? Well, suppose there's no ice cream mountain. Well, the only way the first clown can succeed in their plan, right, the green clause isn't being satisfied, so the only way they can succeed is via the blue clause, via ensuring there are 3 balloons in the room at noon. And for clown number 2, if clown number 2 is going to succeed, well, the green clause isn't satisfied, so the only way for them to succeed is to ensure there are exactly 2 balloons in the room at noon, right? But there can't be exactly 2 balloons and also exactly 3 balloons in the room, so that's a contradiction. So there must be an ice cream mountain outside the room at noon. Okay, so if you think about it, this simple puzzle essentially has the same logic of our puzzle with infinitely many clowns, right? What's really going on in the puzzle with infinitely many clowns is that the clowns start out with plans that are basically inconsistent with each other, unless, right, we just have this sort of escape clause where if there is an ice cream mountain that's fine. Okay, so you might say, well, hang on, this was a little bit too easy, right? Because in my puzzle with the 2 clowns, the 2 clowns are trying to ensure that incompatible things happen in the room at the very same time, right? So we understand what's going to go wrong there, right? So if there's no ice cream mountain, their things are going to be incompatible, and we know what's going to go wrong, right? They both come at noon. One of them is trying to make sure there are 2 balloons. One of them is trying to make sure there are 3 balloons. Both these things can't happen at noon, okay? Isn't what's puzzling about the original puzzle is that these clowns come into the room at different times, right? They're not clashing with each other. Each of them is entering the rooms and trying to put some balloons at a different time. Okay, so I want to say 2 things about that. One is, remember our previous lesson. From the previous lesson, we know that some of the reasons that clowns can fail is not just because another clown is sort of jostling them at the same time, right? There are many, many reasons they can fail that might have nothing to do with the other clowns. But I also want to say this, in addition, that we can also have variants of the puzzle that have finitely many clowns, and these clowns are going to try to do things at different times. Okay, so let's quickly see a version of that. So this version 2 will have only 2 clowns. So clown number 1 comes in at, clown number 2 comes in at noon, and clown number 1 comes in at 1. And here are their plans. Clown number 1 plans to put balloons in the room if and only if clown number 2 puts balloons in the room. And clown number 2 plans to put balloons in the room if and only if clown number 1 does not put balloons in the room. Okay? So if you think about it, they cannot both succeed in their plans, right? So basically, clown 1 wants them to do the same thing, either for both of them to put balloons or for both of them to refrain from putting balloons, and clown number 2 wants them to do different things, so these plans are incompatible. They can't both succeed. And in this case, the plans are just inconsistent, but you can by now see how to construct a variant of this where instead we tweak their plans so there is an escape clause with an ice cream mountain, and then they could succeed, but that would entail that there is an ice cream mountain in the room. Okay, so we seem to have a variance of the puzzle where the finitely many clowns, they come in at different times, and we're still going to ensure there's an ice cream mountain in the room. Okay, you might think this still isn't quite as good as our puzzle with infinitely many clowns, right? So here's one thing that was weird about the original puzzle. In the original puzzle, every clown, when they walked into the room, their plan only depended on conditions that already happened in the past, right? They only needed to check whether there was an ice cream mountain there earlier and whether earlier clowns have put balloons. But in this case, we have one clown, clown number 2, that makes a plan that depends on something that's going to happen in the future, right? It depends on what clown number 1 is going to do in the future. So you might think this is a bit dodgy. Maybe the only way for clown number 2 to carry out this plan is to consult a fortune teller. I'm going to let you in on a little secret. It's not just infinity that's not that special. It's also fortune tellers that are actually not that special. So in fact, all of you have fantastic abilities to tell some things that are going to happen in the future. And we make plans all the time dependent on future events. Okay? So some days I am trying to decide whether to cook dinner or not, but my partner left a message on the fridge saying that he will cook dinner tonight. So I know based on this future event that he will cook dinner tonight, I decide not to cook dinner earlier in the day. Okay? And I just checked and noticed a future event. Tomorrow, it will be Friday, and I will be teaching a class. So based on these future events, I'm now going to prepare my class for tomorrow. Okay? So we make plans in this way all the time, and exactly the same thing might be true of these clowns, right? So clown number 2 might have a lot of very mundane way to determine what clown number 1 is going to do. Okay, maybe clown 1, which is a very trustworthy clown, left a note on the fridge promising they're going to put balloons on the fridge at 1. Or maybe clown number 2 has just found out that clown number 1 has recently developed a severe allergy to balloons. So they're sure when clown number 1 is going to come in at 1, they're not going to put in any balloons. Okay, so I think this puzzle is actually not that different from our puzzle about infinitely many clowns. Okay, so the conclusion is that the original puzzle wasn't really essentially about infinity. I do think infinity played a role in the puzzle, but I think it played a psychological role. It played a role in why we found it so puzzling. And the reason we found it so puzzling is that when we have just 2 clowns, it's very easy for us to see that their plans are inconsistent with each other, or maybe inconsistent unless there's an ice cream mountain. But we're not that good at reasoning about infinity. When we have infinitely many clowns, it takes us more work to figure out what's going on, and we don't immediately see that their plans are just inconsistent with each other. Okay, so this brings me to the end of our lecture. We're going to take a few questions, but before I do so, I'm going to add one more slide that has a few reading suggestions of some of the academic literature on these topics in case any of you want to chase that up. Okay, I'll finish here.